Think about the last time you picked up a paperclip with a magnet. That tiny pull you felt barely noticeable, really, was enough to defy the very force that keeps planets in orbit and galaxies from flying apart. Gravity, the invisible hand shaping the cosmos, is so weak that a child's toy can overpower it. How can something so fundamental, so universal, be so astonishingly feeble? This isn't just a quirky fact, it's one of the deepest mysteries in physics, a puzzle that has stumped scientists for decades. If gravity were just a little stronger, the universe as we know it wouldn't exist. Stars would burn out faster, planets would collapse, and life might never have had a chance to emerge. Yet here we are, in a reality where gravity is 36 orders of magnitude weaker than electromagnetism, a number so large it's almost impossible to comprehend. What makes this even more baffling is that gravity doesn't play by the same rules as the other forces. While electromagnetism and the nuclear forces operate on the quantum scale, gravity seems to exist in its own realm, bending spacetime itself. Why is it so different? Why can't it hold a feather to the ground as firmly as a fridge magnet clings to a door? The answers might lie in hidden dimensions, undiscovered particles, or even the very fabric of the universe itself. Some theories suggest gravity's weakness is a clue, a sign that we're missing a piece of the cosmic puzzle, something lurking just beyond our current understanding. This is the journey we're about to take together, a dive into the heart of one of physics' greatest enigmas. We'll explore the wildest ideas scientists have proposed, from vibrating strings in higher dimensions to the possibility that gravity leaks into other universes. Along the way, we'll uncover why cracking this mystery could rewrite the laws of nature and reveal secrets about the birth of the cosmos. So buckle up. By the end of this, you'll see gravity and the universe in a whole new light. Gravity is the quiet architect of the universe, shaping everything from the way planets dance around stars to how galaxies spiral through the cosmos. It's the reason an apple fell on Newton's head, sparking the realization that the same force keeping the moon in orbit also keeps our feet firmly planted on the ground. Yet for all its cosmic power, gravity is strangely feeble in our daily lives. Jump just a few inches, and you've momentarily escaped Earth's gravitational grip, something no other fundamental force allows so easily. A fridge magnet can lift a paperclip against the pull of an entire planet, and a child's toy balloon charged with static electricity can defy gravity's tug with ease. This odd mismatch becomes even clearer when we look at the numbers. Gravity follows the inverse square law, meaning its strength weakens with distance, but so do electromagnetism and the nuclear forces. The difference is in the starting point. Imagine two protons in an atom's nucleus. The electromagnetic repulsion between them is a staggering 10 to the 36 times stronger than their gravitational attraction. That's a 1 followed by 36 zeros, a number so vast it's hard to even picture. But distance alone doesn't solve the mystery. Even if you cram particles together, gravity remains the weakest player in the game. At the quantum level, where other forces flex their strength, gravity barely registers. While electromagnetism binds atoms into molecules and the strong force glues protons together, gravity's pull is so negligible that it's practically invisible. This bizarre imbalance hints at something deeper. Why does gravity, the force that sculpts galaxies, fade into the background when we zoom in? The answer might lie beyond the familiar laws of physics, in realms where space and time twist in ways we're only beginning to imagine. To understand gravity's puzzling weakness, we need to meet the other players in the cosmic game of forces. Imagine the universe as a stage where 4 fundamental actors shape everything from atoms to galaxies. First, there's electromagnetism, the flashy superstar behind lightning storms, the glow of your screen, and the chemical bonds that make life possible. Then comes the strong nuclear force, the invisible glue holding atomic nuclei together, unleashing the energy of stars with a grip so tight it dwarfs all other forces. And don't forget the weak nuclear force, the quiet orchestrator of radioactive decay, subtly reshaping matter over time. And then there's gravity, the cosmic director, shaping the grandest structures in existence, yet backstage, it's barely a whisper. Picture these forces on a scale where the strong nuclear force scores a perfect 1. Electromagnetism trails close behind, just 100 times weaker. The weak force a billion times fainter, but gravity, it's a 0 followed by a decimal and 36 more zeros before you finally hit a 1. That's not just weak, it's astronomically feeble. A fridge magnet's pull can overpower Earth's gravity on a paperclip, and a simple static shock from your socks outweighs the gravitational tug of an entire planet. Here's the real head-scratcher. At the atomic level, gravity might as well not exist. Electromagnetism dictates how electrons dance around nuclei, crafting every molecule in your body. The strong force binds quarks into protons, fueling stars with nuclear fusion. Even the weak force, despite its name, plays a crucial role in the sun's energy production. But gravity, it's a ghost in the quantum world, too weak to even register. So why does gravity, the force that sculpts galaxies and bends light around black holes, fade into irrelevance on small scales? Some theories suggest gravity isn't weak, it's just diluted. Imagine our three-dimensional universe as a thin slice of something far larger, like a sheet of paper floating in a vast, unseen space. If gravity's influence spills into extra dimensions beyond our perception, its strength in our world could be just a shadow of its true power. Others propose undiscovered particles, like the hypothetical graviton, that might bridge the gap between gravity and quantum physics. The mystery deepens when we consider how perfectly balanced this weakness is. If gravity were even slightly stronger, stars would burn too fast, collapsing the universe into a dense, lifeless crunch. Too weak, and matter would never clump into galaxies. It's as if gravity's feebleness isn't a flaw, it's a finely tuned feature of a universe built for complexity. Solving this puzzle could unlock secrets about the birth of the cosmos, hidden dimensions, or even the nature of reality itself. One thing's certain, gravity's weakness isn't just a quirk, it's a cosmic clue waiting to be deciphered. Einstein turned our understanding of gravity upside down literally. Instead of picturing it as a simple pull between objects, he revealed it as the warping of spacetime itself. Picture a trampoline with a bowling ball at its center. The weight of the ball creates a dip in the fabric, causing smaller objects to roll toward it. That's essentially how massive bodies like planets and stars bend the universe around them, guiding the motion of everything nearby. This elegant idea didn't just solve old mysteries, it predicted astonishing new ones. Starlight, for instance, doesn't always travel in straight lines. When it passes near a massive object like the sun, its path curves, as if space-time itself were a lens. Astronomers saw this firsthand during a solar eclipse in 1919, when stars near the sun's edge appeared slightly out of place, a breathtaking confirmation of Einstein's vision. Black holes take this curvature to the extreme. These cosmic vacuum cleaners warp spacetime so intensely that not even light can escape their grasp. Their gravitational pull is anything but weak, shredding stars and bending the fabric of reality into a singularity. Yet here's the paradox. While general relativity paints gravity as a cosmic sculptor on large scales, it doesn't explain why this same force becomes utterly insignificant in the quantum realm. Einstein's equations work flawlessly for galaxies and black holes, but they collapse when applied to the tiniest particles. At that scale, gravity's weakness isn't just noticeable, it's baffling. Electromagnetism and the nuclear forces dominate, leaving gravity as a faint whisper in the background. This gap hints at something profound. General relativity describes how gravity behaves, but it doesn't tell us why it's so feeble compared to other forces. Einstein spent his later years searching for a unified theory that could bridge this divide, but the puzzle remains unsolved. Some physicists speculate that gravity's apparent weakness might be a clue, a sign that we're missing a key piece of the cosmic framework. Perhaps gravity's strength is spread across hidden dimensions we can't perceive, or maybe it's tied to particles we haven't yet discovered. Until we crack this code, gravity's paradoxical nature, so mighty on cosmic scales, yet so fragile up close, will keep pulling us deeper into the mystery. At the scale of atoms and particles, the rules of the game change dramatically. Here in the quantum realm, particles flicker in and out of existence. Electrons exist in multiple places at once, and forces like electromagnetism dominate with staggering intensity. Yet gravity, the force that shapes galaxies, is conspicuously absent from the party. It's as if the quantum world barely notices gravity's existence. Picture a ghost drifting effortlessly through walls, untouched by the solid barriers around it. That's gravity in the quantum realm, a whisper in a thunderstorm, a feather's touch against a raging river. This isn't just a minor inconsistency, it's a fundamental clash between two pillars of physics. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime, a smooth fabric bending under the weight of mass. But quantum mechanics paints reality as a chaotic dance of discrete particles and probabilities. When scientists try to merge these two frameworks, the equations explode into nonsense. Gravity, so elegantly described by relativity, simply refuses to play by quantum rules. Enter the graviton, a hypothetical particle that could carry the force of gravity, just as photons carry electromagnetism. If gravitons exist, they'd be the universe's most elusive messengers, interacting so weakly with matter that detecting them borders on fantasy. Imagine trying to hear a single note of a flute in the middle of a hurricane. That's the challenge physicists face in hunting for gravitons. Their potential existence hints at a quantum side to gravity, but their invisibility only deepens the mystery of why gravity fades into the background at tiny scales. This is where string theory steps in, offering a radical solution. What if particles aren't tiny dots but vibrating strings, each oscillation corresponding to a different force? In this framework, gravity's feebleness could stem from its vibrations leaking into hidden dimensions like sound escaping through an open window. String theory weaves gravity into the quantum tapestry, but it comes at a cost, a universe with 10 or 11 dimensions, most of them curled up too small for us to perceive. The stakes couldn't be higher. Unifying gravity with quantum mechanics wouldn't just solve a theoretical puzzle, it could rewrite our understanding of reality. Black holes, the birth of the universe, even the nature of time itself might look different through this new lens. Until then, gravity's quantum silence remains one of science's most tantalizing enigmas, a quiet challenge whispered across the scales of existence. String theory offers one of the most daring explanations for gravity's puzzling weakness. What if we're only experiencing a fraction of its true strength? Imagine dipping your hand into a pond and watching ripples spread outward in every direction. Now picture those ripples not just moving across the surface, but also leaking into unseen depths below. That's the core idea here. Gravity's influence might be spilling into hidden dimensions beyond the three we experience every day. while electromagnetism and the nuclear forces stay tightly confined to our familiar spatial dimensions. Length, width, and height gravity could be stretching into these extra folds of reality, diluting its power in our observable universe. Think of it like a flashlight beam. Shine it against a wall in a dark room, and the light appears bright and concentrated. But if that same beam were split, with half its rays escaping into an invisible corridor, the light on the wall would seem dimmer. In this scenario, gravity isn't inherently weak, we're just missing most of its effect. Other forces, by contrast, might be like laser pointers aimed solely at our three-dimensional wall, appearing stronger because they're not leaking away. String theory proposes these extra dimensions aren't science fiction but mathematical necessities. To make the equations work, the universe might need as many as 10 or 11 dimensions, most of them curled up so tightly that even atoms can't perceive them. Picture a garden hose lying on the ground. From a distance, it looks like a simple line, one dimension. But up close, you see its circular surface, a second dimension hidden from the broader view. If gravity's ripples can traverse these microscopic, coiled-up dimensions, it would explain why we only feel a faint echo of its full strength. Of course, this idea isn't without its skeptics. After all, no experiment has ever detected a whiff of these extra dimensions. Particle colliders like the Large Hadron Collider have searched for signs of them, perhaps missing energy that could hint at gravity slipping into unseen realms, but so far the results have been silent. Some critics argue that without observable proof, extra dimensions remain a beautiful but unverified hypothesis. Yet the elegance of this solution keeps physicists intrigued. If true, it wouldn't just solve the mystery of gravity's weakness, it could revolutionize our understanding of reality. Black holes, the Big Bang, even the nature of dark matter might look completely different through this lens. And string theory isn't the only game in town. Alternative ideas like the brain world scenario suggest our entire universe could be a three-dimensional brain floating in a higher dimensional space, with gravity as the only force able to cross between them. Other theories take entirely different approaches. Loop quantum gravity, for instance, sidesteps extra dimensions altogether, proposing that spacetime itself is woven from tiny, discrete loops. Here, gravity's weakness might arise from its quantum structure interacting differently with matter. Then there's the possibility of undiscovered particles or fields subtly altering gravity's behavior at small scales. What's remarkable is how each theory, in its own way, turns gravity's feebleness into a clue, a fingerprint of deeper laws waiting to be uncovered. Whether through hidden dimensions, quantum twists, or something entirely unexpected, the search for answers is far from over. And that's the thrill of it. Gravity's weakness isn't just a gap in our knowledge. It's an invitation to explore the edges of reality itself. The hierarchy problem is like standing at the base of Mount Everest and noticing a single grain of sand next to your shoe, then wondering why nature built one so incomparably larger than the other. In physics, this isn't just a curious observation. It's a glaring inconsistency in the very fabric of reality. Gravity's weakness isn't merely a quirk, it's an anomaly that shakes our understanding of how the universe balances its forces. Take the Higgs boson, for instance. This particle, discovered in 2012, gives mass to everything it touches, from electrons to elephants. But here's the twist. The Higgs' own mass should, in theory, be dragged up to unimaginable scales by quantum fluctuations, making gravity even more dominant. Yet somehow it stays feather-light, as if an invisible hand is fine-tuning the numbers with impossible precision. This is the heart of the naturalness problem, the unsettling sense that the universe's constants seem arbitrarily set, like dials adjusted just right for life to exist. If gravity were even slightly stronger, stars would burn out in a cosmic blink. If the Higgs mass were heavier, atoms wouldn't form. The numbers feel too perfect, as if the cosmos rolled a million-sided die and landed on the one outcome that allows galaxies, planets, and us. Enter supersymmetry, an elegant but unproven theory that could solve this riddle. It proposes every known particle has a hidden twin, a superpartner that cancels out the extreme quantum fluctuations plaguing the Higgs. Picture a seesaw perfectly balanced by an unseen weight on the other side. If these superparticles exist, they'd not only explain gravity's feebleness, but also hint at a grand symmetry woven into reality's blueprint. Yet after decades of searching, colliders have found no trace of them, leaving physicists to wonder, is supersymmetry hiding in dimensions we can't probe, or is nature's solution even stranger? The hierarchy problem isn't just about gravity's weakness, it's a doorway to questions that redefine reality. Are we missing particles? Do unseen dimensions smooth out the imbalances? Or is the universe fine-tuned by some deeper principle we've yet to uncover? Every unanswered question pulls us closer to the edge of physics, where the ordinary rules dissolve and the extraordinary begins. Supersymmetry whispers a tantalizing possibility that every particle we know has a hidden twin, a shadowy counterpart balancing the cosmic scales. Imagine a world where electrons, quarks, and photons each have an undiscovered partner, like dancers waiting in the wings. These sparticles, as physicists call them, could be the missing piece that explains why gravity is so weak while other forces dominate. Here's how it works. Quantum fluctuations constantly jostle the Higgs boson, threatening to inflate its mass to unimaginable levels. But if sparticles exist, their interactions would perfectly cancel out these wild swings, like two waves crashing together and leaving calm water behind. The Higgs stays light, and gravity's feebleness suddenly makes sense. It's not weak by accident, but because the universe is built on this delicate symmetry. Picture a seesaw with the known particles on one side and their superpartners on the other. If the seesaw stays level, the hierarchy problem, the bizarre gap between gravity's strength and other forces, could vanish. Sussy doesn't just tidy up the math. It weaves gravity into the same quantum tapestry as electromagnetism and the nuclear forces, hinting at a unity deeper than we've ever imagined. Yet for all its elegance, supersymmetry remains a ghost. The Large Hadron Collider, the most powerful particle smasher ever built, has hunted for sparticles for over a decade. So far, the detectors have stayed silent. No squarks, no leptons, no gluinos. Some physicists argue Sussy might still be hiding, perhaps just beyond the LHC's energy reach, or in ways too subtle for current experiments to spot. Others whisper that nature might not play by these rules after all. This silence leads us to an even wilder idea, the multiverse. If Sussy isn't the answer, maybe gravity's weakness isn't a puzzle to solve but a cosmic accident. In an infinite sea of universes, each with different laws and constants, ours just happens to have the right imbalance for stars, planets, and life. It's a humbling thought that gravity's feebleness might not stem from elegant symmetry, but from sheer luck in a vast, uncaring expanse of realities. The multiverse hypothesis doesn't so much solve the hierarchy problem as dissolve it. Instead of asking why gravity is weak, we'd accept that in most universes it isn't, and we simply live in the rare one where it is. It's like finding a single grain of sand perfectly shaped like a castle on an endless beach. No law dictated its form, it just happened. Critics argue this swaps one mystery for another, trading mathematical elegance for philosophical speculation. But in the absence of sparticles, the multiverse remains a provocative escape hatch, one that forces us to confront whether gravity's weakness is a clue, a coincidence, or something beyond our current imagination. Between supersymmetry's unfulfilled promise and the multiverse's dizzying scope, one thing is clear: the hierarchy problem isn't just about numbers on a page. It's a window into how deeply we're willing to question reality, and how many layers of the cosmic onion we're prepared to peel back. What if gravity's weakness isn't a puzzle to solve, but a cosmic roll of the dice? Picture a vast casino with infinite slot machines, each representing a universe with its own unique set of physical laws. Most machines spit out combinations where gravity is too strong or too weak for stars, planets, or life to exist. But in a handful, the dials land just right. Gravity is feeble enough for galaxies to form slowly, stars to burn steadily, and life to emerge. We're not special. We're just the lucky ones who happen to be in a universe where the numbers lined up. This is the multiverse hypothesis in a nutshell, an ocean of realities where ours is simply the rare drop that allows us to ask the question in the first place. This idea leans on the anthropic principle, the notion that the universe's laws appear fine-tuned for life because, well, we're here to observe them. It's like a lottery winner marveling at their odds without realizing someone had to win. If countless universes exist, each with random constants, it's no surprise that at least one would stumble into the Goldilocks zone where gravity's weakness permits complexity. No deeper law or symmetry is needed. It's pure statistics. Critics, of course, raise a valid point. How do you test a theory that posits an infinite number of unobservable universes? Without evidence, the multiverse can feel less like science and more like philosophy dressed in equations. Even proponents admit it's a last resort, a way to make sense of fine-tuning when no other explanation emerges. But there's a certain elegance to its humility. Instead of insisting nature must conform to our desire for neat, unified laws, it accepts that randomness might be woven into the fabric of reality. Yet the multiverse isn't the only path forward. While it offers a provocative escape from the hierarchy problem, physicists haven't given up on finding answers within our own universe. Experimental approaches are pushing the boundaries of what we can observe. Some hunt for subtle deviations in gravity's behavior at microscopic scales, where hidden dimensions or quantum effects might leave fingerprints. Others design tabletop experiments to measure gravity's pull between tiny masses, searching for anomalies that could hint at new physics. And then there's the quest to detect gravitational waves from the earliest moments of the Big Bang, which might carry echoes of higher dimensions or exotic particles. The beauty of this mystery is that it refuses to be boxed in. Whether gravity's weakness stems from a multiverse's chaos, a yet undiscovered symmetry, or something beyond our current imagination, the search itself is reshaping how we see reality. Every dead end, every unexpected result is a signpost pointing toward deeper truths, and that's the thrill, not just in solving the puzzle, but in realizing how much grander the cosmos might be than we've dared to dream. The Large Hadron Collider isn't just a machine, it's a time machine, a microscope, and a cosmic detective all rolled into one. Buried beneath the border of France and Switzerland, this 17-mile ring of superconducting magnets smashes protons together at nearly the speed of light, recreating conditions unseen since the universe's first trillionth of a second. And in those fleeting moments of collision, physicists scour the debris for clues that might finally explain gravity's baffling weakness. Could a spray of unexpected particles reveal hidden dimensions? Might a missing energy signature hint at gravity leaking into other realms? Every experiment is a high-stakes gamble, a chance to catch nature in a rare, unguarded moment. Take supersymmetry, for example. If sparticles exist, the LHC's detectors should catch them flickering into existence amid the chaos of particle collisions. Imagine sifting through the aftermath of a fireworks explosion, searching for a single, unique spark that shouldn't be there. That's the painstaking work happening at CERN. Yet after years of data, enough to fill stacks of hard drives reaching from Earth to the Moon and back, no definitive superpartners have emerged. Hopes flared in 2015 when a curious bump in the data hinted at a particle 6 times heavier than the Higgs, but like a mirage, it vanished under closer scrutiny. These phantom signals are both exhilarating and agonizing, teasing answers before slipping through the fingers of science, but the hunt is far from over. The LHC's upcoming high-luminosity upgrade, set for 2029, will supercharge its capabilities, producing collisions at 10 times the current rate. More collisions mean more chances to spot the extraordinary, perhaps even gravitons, the hypothetical carriers of gravity's force. Picture trying to hear a whisper in a crowded stadium. The upgraded LHC will be like turning down the noise while cranking up the sensitivity. And it's not just about brute force. Researchers are refining triggers and algorithms to spot subtler anomalies, like minuscule deviations in how particles scatter, which could betray gravity's secrets. Meanwhile, astrophysics offers its own clues. Gravitational waves, those ripples in spacetime first detected in 2015, are opening a new window into the universe's most violent events. When black holes collide, their gravitational wave signatures could carry hidden imprints of extra dimensions or exotic particles. Even the cosmic microwave background, the afterglow of the Big Bang, might hold patterns suggesting why gravity plays by different rules. The stakes couldn't be higher. Solving gravity's weakness wouldn't just fill a textbook gap. It could unlock technologies beyond our wildest dreams. Imagine harnessing gravitational waves for communication, or manipulating extra dimensions to engineer new states of matter. More profoundly, it would rewrite our origin story, revealing whether gravity's feebleness is a cosmic accident, a feature of hidden physics, or a signpost to realities we've yet to imagine. The LHC and its successors are our best shot at turning speculation into revelation, one collision at a time. Black holes are gravity's masterpiece, cosmic furnaces where the force's true power is on full display. These monstrous objects warp spacetime so profoundly that not even light can escape their grasp, bending the fabric of reality into a singularity. Yet even here, in gravity's strongest domain, its paradoxical weakness lingers. The very existence of black holes hinges on a delicate balance. If gravity were just a fraction stronger, stars might collapse too quickly for galaxies to form. If it were weaker, black holes might never ignite at all. It's as if the universe calibrated gravity's strength with surgical precision, leaving us to wonder why this number and not another. Enter gravitational waves, the universe's quiet messengers. When two black holes spiral into each other, they send ripples through spacetime itself, like tremors from a distant earthquake. In 2015, the LIGO Observatory detected these waves for the first time, confirming Einstein's century-old prediction in stunning detail. But the real magic lies in the subtleties. Gravitational waves aren't just proof of black holes, they're a testing ground for gravity's deepest secrets. Tiny deviations in their patterns could betray cracks in Einstein's theory, hints of quantum gravity lurking at the edges of our understanding. Imagine listening to a symphony and catching a single note out of tune. That's the precision needed to spot gravity's quantum whispers in the chaos of colliding black holes. Then there's the enigma of primordial black holes, hypothetical relics from the Big Bang, some no heavier than an asteroid yet denser than a star. These ancient objects could be hiding in plain sight, masquerading as dark matter. If they exist, they'd weave gravity's weakness into the cosmos's very architecture, explaining why galaxies rotate faster than visible matter alone can account for. Picture a universe where dark matter isn't an exotic particle but a swarm of invisible black holes, remnants of a time when gravity's rules were still being written. Dark matter itself adds another layer to the mystery. Though it outweighs normal matter 5-to-1, it barely interacts with gravity's siblings electromagnetism and the nuclear forces. It's as if dark matter is deaf to everything but gravity's faintest hum, amplifying its influence on cosmic scales while remaining ghostly in our detectors. Some theories suggest dark matter's silence might hold clues to gravity's quantum side, or even hint at extra dimensions where gravity's strength is diluted. Every collision, every ripple, every unseen speck of dark matter is a piece of the puzzle, one that could rewrite our understanding of the universe's weakest, yet most far-reaching force. Dark matter is the universe's silent puppeteer, an invisible hand shaping galaxies with a gravitational grip that defies explanation. Look at any spiral galaxy spinning gracefully through space, and you'll notice something strange. The stars at its outer edges whip around just as fast as those near the center. According to the laws of gravity, this shouldn't happen unless there's far more mass tugging on them than we can see. Enter dark matter, the mysterious substance whose gravity holds galaxies together like cosmic glue, outweighing visible matter 5-to-1. Yet for all its gravitational muscle, dark matter refuses to interact with light, electromagnetism, or even the nuclear forces. It's as if the universe built a ghost capable of bending spacetime but utterly indifferent to everything else. This bizarre disconnect might hold the key to gravity's weakness. If dark matter particles exist, they'd be the universe's ultimate introverts, passing through planets and people like phantoms, leaving only gravity as their calling card. The leading candidates, weakly interacting massive particles, are hypothesized to be heavy, slow-moving relics from the Big Bang. Their sheer mass could explain dark matter's gravitational heft, while their reluctance to interact with ordinary matter would align with gravity's faint presence in the quantum realm. Then there are actions, hypothetical particles so light and elusive they could form a cosmic fog, subtly warping spacetime on galactic scales. Yet after decades of hunting, detectors buried deep underground in abandoned mines and even in space have come up empty. Labs like Xenon and LUX, designed to catch the rare collision between a WIMP and an atom, have recorded nothing but silence. Action searches, using ultra-sensitive magnetic fields to convert these phantom particles into detectable photons, have similarly found no trace. This absence is more than frustrating, it's a clue. If dark matter doesn't behave as predicted, perhaps gravity's feebleness isn't just about particles we can't find, but about dimensions or forces we've yet to imagine. Now shift your gaze from the darkness between galaxies to the emptiness itself. Dark energy, an even more enigmatic force, is pushing the universe apart at an accelerating rate. Unlike dark matter's gravitational pull, dark energy seems to be a property of space itself, a cosmic anti-gravity stretching the fabric of reality. Here's where the plot thickens. If dark energy's repulsive force grows while gravity's attractive pull remains weak, the universe could be headed toward a future where galaxies are ripped apart, stars vanish into isolation, and space-time itself becomes a vast, empty void. The eerie symmetry is hard to ignore. Dark matter amplifies gravity's influence on cosmic scales while remaining ghostly in our detectors. Dark energy counters gravity entirely, its strength seemingly fine-tuned to a value just small enough to allow galaxies to form but large enough to doom the universe to expansion. Together, they paint a picture where gravity's weakness isn't an accident. It's a delicate balance between two invisible forces, one sculpting the cosmos and the other unraveling it. Whether this balance is a clue to deeper physics or a cosmic coincidence remains one of the greatest unsolved riddles of all. Imagine the universe as a cosmic tug of war, with gravity on one side and dark energy on the other. For billions of years, gravity held the upper hand, pulling galaxies together, sculpting clusters, and weaving the large-scale structure of the cosmos. But around 5 billion years ago, something shifted. Dark energy, an enigmatic force woven into the fabric of space itself, began to dominate, pushing the universe apart at an ever-increasing pace. This isn't just a gradual expansion, it's an acceleration, as if the cosmos stepped on the gas pedal with no intention of slowing down. And here's the twist: gravity's weakness might be the very reason dark energy is winning. Think of it like a balloon inflating. Gravity acts like the rubber's tension, trying to pull everything back together. Dark energy, on the other hand, is the air being pumped in, stretching the balloon's surface relentlessly. The weaker the rubber, the easier it is for the air to take over. In our universe, gravity's feebleness gives dark energy the upper hand, allowing empty space to push galaxies apart faster than gravity can reel them in. This bizarre dynamic raises a haunting question. Is gravity weak because dark energy is strong, or is it the other way around? At the heart of this mystery lies the cosmological constant, Einstein's infamous greatest blunder, which he later discarded but might have been right about all along. This constant represents the energy of empty space, a repulsive force embedded in the vacuum itself. Quantum physics tells us that even a perfect vacuum should fizz with particles popping in and out of existence, each contributing a tiny bit of energy. Add them all up, and the vacuum's energy density should be enormous enough to rip atoms apart before they could even form. Yet observations show dark energy's effect is staggeringly small, about 120 orders of magnitude weaker than quantum theory predicts. This mismatch, known as the vacuum energy puzzle, is one of the worst in physics. Some theories suggest gravity's weakness might be the universe's clever workaround. If gravity were stronger, dark energy's push would have overwhelmed matter long before galaxies could take shape. Instead, gravity's subtle pull allowed structures to form just long enough for stars, planets, and life to emerge before dark energy took the reins. It's as if the cosmos threaded a needle, too much gravity, and the universe collapses, too little, and it flies apart before complexity can arise. But what if dark energy isn't constant at all? Alternative models propose it could evolve over time, growing stronger or weaker in ways we haven't yet detected. String theory offers another wild possibility. Dark energy might be tied to the way extra dimensions stabilize or decay, subtly altering the expansion rate of our visible universe. Then there's the chance that dark energy and gravity are two sides of the same coin, linked by some deeper symmetry we've yet to uncover. The stakes couldn't be higher. If dark energy continues to accelerate the universe's expansion unchecked, distant galaxies will eventually vanish beyond an unreachable horizon, leaving our descendants with a sky devoid of stars. Gravity, the force that built the cosmos, could one day be reduced to a footnote in a lonely, fading universe. Yet this bleak future also holds a clue. Understanding why dark energy dominates might finally reveal why gravity is so weak, and whether the two are locked in a dance that's been choreographed since the Big Bang. As physicists probe this puzzle, they're not just studying the fate of the universe. They're asking whether gravity's feebleness is a fluke, a necessity, or a signpost to realities beyond our own. Every observation, from supernova to the cosmic microwave background, brings us closer to an answer, one that could rewrite the laws of physics and reveal the hidden rules that have shaped everything from atoms to galaxies. While string theory dances with extra dimensions, another bold idea takes a radically different approach: loop quantum gravity. Picture spacetime not as a smooth, continuous fabric, but as a tapestry woven from countless tiny, indivisible loops. These loops, each a billion trillion times smaller than an atom, form a network so fine that their collective structure creates the illusion of the seamless universe we experience. In this framework, gravity's weakness could stem from the way these loops interact like threads in a cosmic quilt, their connections determining how strongly the fabric of reality resists distortion. Unlike string theory, loop quantum gravity doesn't need hidden dimensions to explain gravity's feebleness. Instead, it suggests that spacetime itself has a granular quantum structure, with gravity emerging as a sort of stitching between these fundamental loops. Think of it like comparing a steel cable to a loosely knitted scarf. The cable's strength comes from its tightly interwoven strands, while the scarf's gaps make it far less resistant to pulling. If spacetime's loops are knit together in a particular way, perhaps with gaps or asymmetries in their quantum connections, gravity's pull might naturally turn out weaker than other forces. This idea flips the script. Gravity isn't diluted by leaking into other dimensions. It's inherently delicate because of how spacetime is built at the tiniest scales. But here's the catch. Like string theory, loop quantum gravity remains untested. Its equations beautifully describe how spacetime might quantize, but without experimental proof, it's a cathedral built in the abstract. Some physicists argue that its focus on geometry rather than particles or strings could make it more compatible with Einstein's general relativity, offering a cleaner path to unifying gravity with quantum mechanics. Others counter that its lack of extra dimensions makes it mathematically rigid, leaving little room for the flexibility needed to explain all of nature's forces. This is where the holographic principle enters the stage, blending ideas from both camps. Imagine the universe as a cosmic hologram, where all the information needed to describe three-dimensional reality is encoded on a two-dimensional surface at its boundary. In this wild vision, gravity's weakness might arise because it's not a fundamental force at all, but a shadow, a projection of deeper interactions playing out on the universe's edge. Picture a movie screen. The images seem three-dimensional, but they're really just patterns of light on a flat surface. If gravity works similarly, its feebleness could reflect the fact that it's not real in the way other forces are, but an emergent property of information flowing through the cosmos. The holographic principle doesn't just challenge our notions of gravity, it redefines reality itself. And while it sounds like science fiction, it's grounded in rigorous math, including insights from black hole thermodynamics. Yet for all its elegance, it shares the same hurdle as its rivals. Without a way to test these ideas, they remain thrilling possibilities rather than proven truths. That's the frontier of physics, a realm where the answers to gravity's greatest mystery might lie just beyond the reach of our current tools, waiting for the next breakthrough to bring them into focus. The holographic principle turns reality inside out. What if everything we see, touch, and feel is just a grand illusion? Imagine a shadow puppet cast on a wall. The shapes appear three-dimensional, full of depth and movement, but they're really just flat silhouettes manipulated by unseen hands. Now stretch that idea to the cosmos. Our universe, with its galaxies, black holes, and swirling nebulae, might be nothing more than a projection, a hologram encoded on a distant, two-dimensional surface. In this bizarre framework, gravity isn't a fundamental force but an emergent phenomenon, a side effect of information dancing on the universe's outer edge. This isn't science fiction, it's a serious theory with roots in black hole physics. When scientists calculated how much information a black hole can hold, they found it's proportional not to its volume but to its surface area, as if all the data inside were somehow painted on its event horizon. The AD/S/CFT correspondence, a mathematical breakthrough in string theory, takes this further. It suggests a perfect equivalence between a higher dimensional space, like our universe, and a lower dimensional boundary where gravity might not even exist. Picture a snow globe. The three-dimensional scene inside is completely described by equations written on its two-dimensional glass surface. If true, gravity's weakness could simply reflect its status as a shadow real enough to shape galaxies, but fundamentally insubstantial. The implications are staggering. If gravity emerges from a boundary we can't see, it might explain why it's so feeble compared to other forces. Electromagnetism and the nuclear forces could be native to our three-dimensional world, operating at full strength, while gravity is more like an echo, a distant ripple from a deeper layer of reality. This would also solve a thorny problem in physics: how to reconcile gravity's smooth, geometric nature in general relativity with the chaotic, quantized world of particles. In the holographic view, spacetime itself isn't continuous but pixelated, with gravity arising from the way these pixels interact at the quantum level. Of course, the holographic principle remains speculative. No experiment has yet offered proof, and some critics argue it's more philosophy than physics. But its elegance is undeniable. By reframing gravity as an emergent property, it sidesteps the need for extra dimensions or undiscovered particles, offering a radically different path to unification. It's also deeply humbling, a reminder that our perception of reality might be as limited as a goldfish's view from its bowl. To appreciate how far we've come, rewind to the 1970s, when physicist Jacob Bekenstein first proposed that black holes have entropy, a measure of disorder tied to their surface area. At the time, the idea was heresy. Black holes were thought to be simple, sterile objects, but Stephen Hawking soon showed they emit radiation, warming the door to quantum gravity. Fast forward to the late 90s, when Juan Maldacén's work on AD/CFT gave the holographic principle mathematical teeth, linking string theory to quantum field theory in a way that made physicists gasp. Today, labs are searching for hints of holography in the cosmic microwave background, and even tabletop experiments simulating quantum black holes. Whether the holographic principle holds the key to gravity's weakness or not, it's already reshaped how we think about space, time, and information. It suggests that the universe might be more like a cosmic mirage, a shimmering projection of something far stranger, lurking just beyond the edges of our perception. And if that's true, the real mystery isn't why gravity is weak, but why we ever thought reality was as solid as it seems. Newton's famous apple wasn't just a fruit, it was the spark that lit the fuse of modern physics. When it struck him on the head, or more likely, just fell nearby, it led to a revolutionary idea. The same invisible force pulling the apple down also held the moon in orbit. His law of universal gravitation, written in 1687, was a masterpiece of simplicity. A single equation could predict the motion of planets, the ebb and flow of tides, even the arc of a cannonball. For centuries, it seemed like the final word, but here's the twist: Newton himself wasn't satisfied. He spent years chasing alchemical recipes, searching for hidden forces in nature, scribbling notes about a mysterious ether he believed permeated space. To him, gravity's how was clear: objects attracted each other, but the why remained a haunting mystery. Fast forward to today, and Newton's gravity feels almost quaint. Not wrong, just incomplete, like a black and white sketch of a world we now see in Technicolor. Einstein showed us gravity isn't a pull but the bending of space-time, a cosmic trampoline warped by mass. Quantum mechanics revealed a subatomic realm where gravity barely registers, and yet, despite all our advances, we're no closer to answering Newton's deepest question: why does gravity work this way? The irony is delicious. The force Newton codified with such precision is now the biggest outlier in physics, refusing to play nice with the other three fundamental forces. His era brimmed with certainty. Laws were absolute, the universe a clockwork machine. Ours thrives on uncertainty, where 95% of the cosmos is made of dark matter and energy we can't explain. But that's how science grows. Every final answer is just a stepping stone to the next mystery. What's thrilling is how far we've come in testing the untestable. Newton could only watch apples fall. We're flinging particles at near light speeds, listening for space-time ripples from colliding black holes, and probing the vacuum of space for quantum whispers. The apple's lesson endures. Sometimes the simplest observations are falling fruit. A magnet lifting a paperclip hold the keys to the universe's grandest secrets. And if history's any guide, today's open questions are tomorrow's revolutions. In a basement beneath the University of Washington, physicists are playing the universe's quietest game of tug-of-war. Their weapon, a pair of gold-plated weights, each no larger than a grain of rice, suspended in near-perfect vacuum. The goal, measure the gravitational pull between these minuscule masses, a force so weak it's dwarfed by the static cling of a stray electron. This isn't just an exercise in precision, it's a hunt for clues about gravity's quantum nature, conducted at scales where the fabric of reality might finally reveal its secrets. The challenge is mind-boggling. At these microscopic distances, gravity's pull is roughly a billionth of a Newton, comparable to the weight of a single bacterium. To detect it, researchers must silence every competing whisper of interference. The lab's walls are thick with vibration-dampening materials, shielding against footsteps, distant traffic, even the rumble of ocean waves. The apparatus itself floats on a cushion of air, isolated like a jewel in a silent cathedral. One scientist described the work as listening for a feather to drop in a hurricane. Why go to such extremes? Because if gravity behaves quantum mechanically at these scales, it should leave fingerprints, subtle deviations from the smooth, continuous pull predicted by classical physics. Some experiments, like those using ultra-cold neutrons or dangling microscopic cantilevers, aim to catch gravity, quantizing into discrete packets, much like light's photon particles. Others are searching for anomalies in the inverse square law itself, hints that extra dimensions or unseen particles might be altering gravity's strength at tiny separations. The stakes are cosmic. If gravity is quantum, it would bridge the last gap in our understanding of nature's forces, stitching Einstein's spacetime into the subatomic tapestry. If it's classical all the way down, we're back to square one, forced to reconsider whether gravity is even a fundamental force at all. Philosophers weigh in too. Does gravity's stubborn refusal to quantize suggest it's emergent, like temperature or pressure, a collective effect of some deeper, hidden layer of reality? For now, the labs are silent, their delicate instruments humming with anticipation. Every failed vibration, every stray magnetic field is a lesson, tightening the screws on tomorrow's experiments. The answers, if they come, won't arrive with fanfare. They'll slip in quietly, like gravity itself felt long before it's understood. John Wheeler once called gravity the greatest teacher, not because it obeys our equations, but because it constantly defies them. Why does this cosmic weakling, outmuscled by every other force in nature, hold such a profound grip on our imagination? The answer might lie not in the math, but in what gravity's feebleness reveals about the universe's hidden architecture. Richard Feynman marveled at how nature's laws often wear a mask of simplicity, like a magician's trick where the real action happens just out of sight. Gravity's weakness could be that kind of sleight of hand, a clue that the stage we see is far smaller than the theater it's part of. Consider the alternative. If gravity were as strong as electromagnetism, stars would burn through their fuel in mere millions of years, collapsing before life could even stir. Galaxies would clump too tightly, leaving no room for the vast cosmic voids that let light travel billions of years undisturbed. The universe would be a cramped, short-lived affair. No time for planets to cool, for chemistry to experiment, for life to ask why gravity is weak in the first place. This isn't just a quirk of physics, it's a precondition for existence. The more we study it, the more gravity's feebleness looks less like a flaw and more like a signature, a deliberate signature, on the blueprint of reality. Philosophers and physicists alike have wrestled with this idea. Einstein saw gravity's elegance as evidence of a deeper harmony, while quantum pioneers like Niels Bohr argued its weakness might be the price of admission to a universe where uncertainty and possibility reign. Modern thinkers take it further. Could gravity's subtlety be a side effect of something grander, like a holographic universe or a multiverse filtering out unfit realities? The question transcends equations. It's about why the universe feels designed for questions to be asked at all. Culturally, gravity's paradox has seeped into our metaphors. We speak of gravitons to describe weighty ideas, yet we also celebrate the levity that lifts us above life's pull. Artists paint astronauts floating in sublime defiance of Earth's hold, while poets write of love as a force stronger than gravity. Even our myths echo the tension from Icarus falling to Wile-E. Coyote suspended midair, reminding us that gravity's weakness is what makes defiance possible. Perhaps that's the lesson. Gravity's feebleness isn't an oversight, it's an invitation. A universe where gravity was stronger might never have spawned creatures who could marvel at its strength or lack thereof. Every time a child jumps for joy or a scientist launches a probe into the void, they're not just working against gravity's pull. They're proving why its gentleness might be the most profound gift the cosmos ever gave us. Gravity's cosmic mystery isn't just fodder for physicists, it's fuel for storytellers. Take Interstellar's Gargantua, a black hole rendered with such scientific precision that physicist Kip Thorne published papers on its accretion disk's lensing effects. The film's portrayal of time dilation near a black hole wasn't just cinematic flair, it was general relativity in action, wrapped in Hans Zimmer's haunting score. Yet for every Interstellar, there's a Doctor Strange, where the quantum realm bends gravity into psychedelic fractals, trading accuracy for awe. Sci-fi thrives in this tension, stretching the rules just enough to spark wonder without snapping the thread of plausibility. Marvel's Ant-Man shrinking to subatomic sizes, or The Expanse's realistic zero-G battles, these aren't just entertainment. They're stealth physics lessons, smuggling concepts like tidal forces and spacetime curvature into popcorn blockbusters. When Gravity depicted Sandra Bullock tumbling through orbit, audiences viscerally felt Newton's first law: objects in motion stay in motion. The film's inaccuracies, like satellites in wildly wrong orbits, irked astronomers, but its emotional truth, the terror and beauty of weightlessness, made space feel real to millions. This cultural feedback loop is powerful. Sci-fi often dreams up ideas decades before science formalizes them. Arthur C. Clarke envisioned geostationary satellites in 1945. 20 years later, they became reality. Star Trek's communicators inspired flip phones, and Black Mirror's dystopias now haunt AI ethics committees. When films like Arrival wrestle with time's nonlinearity or Contact imagines wormhole travel, they're not just storytelling, they're priming the public to fund the next LIGO or James Webb Telescope. NASA scientists cite Star Wars as career inspiration, and Elon Musk named SpaceX's drone ships after culture novels. Art doesn't just reflect science, it accelerates it. Yet the real magic lies in education. A child watching Wall-E learns about orbital mechanics as the plucky robot pirouettes through space debris. The Martian turns botany and orbital trajectories into life or death drama, proving science isn't sterile equations, it's survival. Even Rick and Morty's absurdist multiverse romps introduce viewers to Schrödinger's cat and neutrino bombs. The best sci-fi doesn't dumb down, it invites curiosity, leaving audiences Googling time dilation or dark matter as the credits roll. The takeaway: Gravity's pop culture journey proves science and art aren't rivals, they're collaborators. Whether it's a black hole's whisper in Interstellar or the quantum realm's trippy visuals, these stories remind us that the universe's deepest mysteries belong to everyone. And sometimes the wildest fiction today becomes tomorrow's textbook. Imagine a classroom where kids aren't just memorizing Newton's laws but wrestling with the gaps in them. Instead of rote calculations, they're holding magnets over paper clips, feeling the eerie mismatch between gravity's cosmic might and its everyday feebleness. This isn't just a science demo, it's a gateway to curiosity. When students see a tiny magnet overpower Earth's gravitational pull, their faces light up with the same wonder that once gripped Newton and Einstein. That's the power of teaching physics not as a closed book but as a living mystery where even the weakest force holds the biggest questions. Great science education doesn't shy away from uncertainty, it leans into it. Take something as simple as a balance scale. Stack weights on one side and a small electromagnet on the other, and suddenly abstract concepts like the hierarchy problem become visceral. Students don't just hear that gravity is weak, they see it, measuring the absurd difference in strength with their own hands. These moments plant seeds. Maybe one kid starts wondering why nature's forces are so unevenly matched. Another might scribble ideas about hidden dimensions in the margins of their notebook. That's how future physicists are made, not by delivering tidy answers, but by sparking the itch to ask better questions. The stakes are higher than ever. We're racing toward a future where understanding gravity's quirks could unlock revolutionary tech. Picture spacecraft propelled by gravitational wave manipulation or energy harvested from quantum fluctuations in spacetime. These aren't just sci-fi dreams, they're possibilities waiting for the next generation to explore. But none of it happens if we teach science as a static set of facts. Kids need to know that today's textbooks contain holes, and those holes are where the magic hides. Consider how we explain the solar system. Traditional models show planets neatly orbiting the sun, as if gravity's job is just to keep things in line. But what if we also talked about the why behind the numbers? Why does Mercury's orbit wobble in ways Newton couldn't explain? Why do black holes bend light but can't hold a candle to the strong force in an atom's nucleus? Framing these as open puzzles, not just problems to solve for homework, turns passive learners into active explorers. The classroom isn't the only place this shift matters. Science communicators play a huge role too. When documentaries and YouTube videos treat gravity's weakness as a cliffhanger rather than a footnote, they invite everyone into the detective work. Neil deGrasse Tyson often says science literacy isn't about knowing facts, it's about understanding how science thinks. And right now, science is thinking hard about why gravity doesn't fit the mold. This approach pays off in unexpected ways. Students who grapple with unsolved mysteries learn resilience. They get comfortable with "I don't know" as a starting point, not a failure. That mindset is gold in a world where the jobs of tomorrow might involve technologies we haven't even imagined yet. After all, the physicists who'll crack gravity's code are probably in middle school right now, tossing paper clips at magnets and wondering why the universe feels so unbalanced. Our job isn't to give them answers, it's to give them tools, wonder, and permission to keep digging. And let's not forget the teachers. They're the unsung heroes here, juggling curricula that often prioritize standardized tests over deep inquiry. But when they carve out space for open-ended exploration, like comparing the gravitational pull between apples to the magnetic force between fridge magnets, they're doing more than teaching physics. They're nurturing the kind of thinkers who might one day redefine it. The ripple effects could be monumental. A student inspired by gravity's puzzle might design the next LEGO, detecting gravitational waves from entirely new phenomena. Another might engineer materials that exploit weak gravitational interactions for medical breakthroughs. The common thread, seeing the gaps in our knowledge not as roadblocks but as launch pads. So here's the challenge. The next time you explain gravity, don't stop at 9.8 meters per second squared. Ask why it's not 9.8 trillion. Watch the confusion, then the curiosity, then the determination flicker across someone's face. That's the moment science education becomes something greater, a torch passed to those who'll carry it into the unknown. Anti-gravity sounds like something ripped straight from the pages of a pulp sci-fi magazine. Floating cars, defying planetary pull with the flick of a switch, entire cities suspended in midair. But here's the twist. While Hollywood treats anti-gravity as a given, real-world physics slams the door shut with a resounding almost. The reason: gravity isn't a force we can shield or negate like magnetism. You can block light with a curtain or stop a bullet with Kevlar, but there's no gravity armor to hide behind. It's woven into spacetime itself, a fundamental thread in the cosmic fabric. Yet the dream persists because gravity's weakness might just leave a crack in the door for the impossible. Take superconductors, those eerie materials where electricity flows without resistance. When cooled to extreme temperatures, they don't just conduct perfectly, they levitate over magnets, locking into place as if pinned by invisible hands. This isn't anti-gravity, but it's the closest thing we've got. A quantum dance where magnetic fields are expelled so completely that the superconductor hovers, frozen in defiance of gravity's pull. The effect, called the Meissner effect, feels like magic, and while it doesn't cancel gravity, it proves that nature has tricks up its sleeve we're only beginning to understand. Then there's the Casimir effect, a stranger phenomenon still. Imagine two metal plates placed microscopically close in a vacuum. Quantum theory says the space between them should fizz with virtual particles popping in and out of existence. But at these tiny distances, only certain wavelengths fit, creating a pressure imbalance that pulls the plates together. Flip the setup just right, and some theorists speculate you could engineer negative energy densities, the stuff needed to warp spacetime in ways that might, hypothetically, mimic anti-gravity. It's not a gravity shield, but it's a hint that the vacuum itself might be manipulated. Of course, the devil's in the details. Negative energy requires conditions so extreme they border on fantasy. And even if achieved, the amounts needed to lift so much as a paperclip would dwarf our current tech. But here's where gravity's weakness becomes tantalizing. If it's truly leaking into extra dimensions or diluted by quantum effects, could we one day find a way to redirect it? Not cancel, just bend, like a magician's mirror tricking the eye. The equations don't forbid it outright, but they don't exactly hand us a blueprint either. The cosmic consequences of cracking this nut would be staggering. Imagine spacecraft that don't fight gravity but sidestep it, slingshotting through warps in spacetime. Or energy systems tapping into the quantum vacuum, harvesting the faint ripples of gravitational potential. It sounds like fantasy, but remember, so did wireless communication and moon landings once. The line between impossible and inevitable often blurs with time. For now, anti-gravity remains a mirage, but the pursuit of it has gifted us superconductors, quantum levitation, and deeper insights into spacetime's flexibility. Maybe that's the real lesson. Sometimes chasing the impossible is what reveals the possible. And if gravity's weakness has taught us anything, it's that the universe loves a good paradox. Picture a universe where gravity isn't the cosmic weakling we know, but a force as fierce as electromagnetism. In this twisted reality, stars don't just burn, they rage. Their nuclear fuel, crushed under gravity's amplified grip, ignites in a frenzied inferno, turning million-year lifespans into fleeting centuries. Galaxies, once sprawling and graceful, collapse into dense knots, their stars packed so tightly that night skies glow like perpetual noon. Planets, too, shrink under the intensified pull, their atmospheres squeezed into thin, suffocating shells. Earth, forget oceans or mountains. Our home would be a compact ball of rock, its surface pressure so extreme that even the hardiest microbes would struggle to cling to existence. This isn't just speculative fiction, it's a window into how precariously balanced our universe really is. Simulations of such a gravity-dominated cosmos reveal a chilling truth. The conditions for life hinge on an almost impossible tightrope walk. Take water, the elixir of life as we know it. In a high-gravity world, liquid water couldn't pool on the surface. It would either boil away under the crushing pressure or freeze into brittle sheets. Complex molecules, the building blocks of biology, would struggle to form, their delicate structures shattered by gravity's relentless tug. Even the atoms themselves would warp, their electron orbits distorted until chemistry as we know it unravels. Artists' renditions of this alternate universe are haunting. Planets loom unnaturally close to their stars, their surfaces cracked and molten under the strain. Skies blaze with the light of hyperactive suns, their lives cut short by gravity's voracious appetite, and in the void between them, black holes form with terrifying ease, swallowing matter before it can ever coalesce into something new. It's a cosmos where structure and chaos trade places, where the very forces that sculpt beauty in our universe instead sculpt oblivion. Yet here's the marvel, our reality dodged this fate. Gravity's feebleness, so easily mocked when a fridge magnet triumphs over an entire planet, turns out to be its greatest gift. Stars burn steadily for billions of years, their slow fusion furnaces cooking the heavy elements needed for planets and life. Galaxies spin at just the right pace to avoid collapsing into chaos, their delicate arms cradling stellar nurseries. And on a tiny blue dot, gravity's gentle hold allows atmospheres to breathe, oceans to ripple, and life to reach for the stars. This fine-tuning isn't just luck, it's a clue. Whether by cosmic accident or some deeper principle, gravity's weakness seems etched into the universe's DNA, a silent enabler of complexity. And that's the real wonder. In the grand tapestry of forces, gravity's quiet humility might be the very thread that holds it all together. So where does this leave us? After peeling back layer after layer of theories, from hidden dimensions to holographic universes, we're still staring at gravity's greatest mysteries with more questions than answers. First, the enigma of extra dimensions. If gravity is truly leaking into unseen realms, why haven't our most sensitive experiments caught even a whiff of them? Particle colliders have slammed protons together with enough energy to recreate conditions a split second after the Big Bang. Yet the detectors remain stubbornly silent. Are these dimensions curled up tighter than we can probe, or is there a flaw in the math? Then there's the quantum gravity puzzle. If spacetime is woven from tiny loops or strings, why does gravity refuse to play by quantum rules while the other forces dance effortlessly? Every attempt to quantize gravity, to chop it into discrete packets like photons, ends in equations that explode into infinity. It's as if the universe is taunting us. dangling a unified theory just out of reach. And let's not forget the hierarchy problem, the Everest of physics. Why is gravity 10 to the 36 times weaker than electromagnetism? That's not just a small gap, it's a cosmic canyon, a number so absurdly large it feels like a clerical error in the universe's blueprint. Supersymmetry promised to balance the scales, but with no sign of sparkles after decades of searching, the mystery only deepens. Could the answer lie in something even stranger, like a multiverse where gravity's weakness is just a random roll of the dice? Or is there a principle we're missing, a hidden symmetry or mechanism that ties it all together? Here's the thrilling part: solving any one of these riddles could unravel the others. Crack the code of quantum gravity, and extra dimensions might snap into focus. Find evidence of hidden dimensions, and the hierarchy problem could suddenly make sense. It's like a cosmic game of Sudoku. Fill in one square, and the rest start falling into place. The stakes couldn't be higher. Unifying gravity with quantum mechanics wouldn't just complete Einstein's unfinished symphony. It could rewrite the rules of reality itself, revealing everything from the birth of black holes to the fate of the cosmos. So as we step back and gaze at the big picture, remember, gravity's weakness isn't just a curiosity. It's a beacon guiding us toward truths that could redefine existence. Whether the answer lies in vibrating strings, warped brains, or something beyond our wildest imagination, one thing's certain: the universe has been hiding its secrets in plain sight, waiting for us to ask the right questions. And the next breakthrough, it might be closer than we think. Gravity's weakness isn't just a curiosity, it's the thread stitching together the universe's greatest mysteries. Think of it like this: that same feeble force you defy every time you jump is also the architect of black holes, the puppeteer of dark matter, and the silent hand guiding the cosmos toward its ultimate fate. Black holes, those cosmic monsters where gravity flexes its full might, paradoxically highlight its weakness. If gravity were stronger, stars would collapse into black holes far more often, littering the universe with them. Too weak, and galaxies might never have formed at all. It's a delicate balance, one that allowed black holes to exist, but not so many that they dominate the cosmos. Then there's dark matter, the ghostly substance that outweighs visible matter 5 to 1. It doesn't interact with light or electromagnetism, only whispering to us through gravity's faint tug. If gravity were stronger, dark matter's influence might have overwhelmed the early universe, preventing galaxies from forming the delicate structures we see today. Instead, gravity's subtle pull let dark matter sculpt the cosmos without crushing it, a cosmic dance where weakness became a virtue. And what of the universe's fate? Dark energy, that mysterious force accelerating the expansion of space, seems locked in a tug of war with gravity. If gravity were stronger, it might have won, pulling everything back into a big crunch. But because it's weak, dark energy is winning, stretching the universe toward a cold, thin fate. Gravity's feebleness isn't just a quirk, it's the reason the universe has a story at all, one with chapters yet to be written. This puzzle isn't just academic. Solving it could be the key to the holy grail of physics, a theory of everything. Unifying gravity with quantum mechanics wouldn't just fill a gap in our textbooks, it could rewrite them, revealing new layers of reality hidden in plain sight. Richard Feynman once said, "The first principle is to not fool yourself, and you are the easiest to fool." It's a reminder to stay skeptical, to question even our most elegant theories, but also to stay hopeful. Every great breakthrough began with someone daring to ask, what if we've been missing something? So what do you think? Does gravity's weakness hint at extra dimensions, or is it a cosmic accident in a multiverse of possibilities? Drop your favorite theory in the comments. We're all part of this grand conversation. And if you love diving into the universe's deepest mysteries, hit subscribe. There's so much more to explore, from the quantum foam beneath our feet to the black holes humming in the void. Look up tonight. The stars aren't just points of light, they're reminders of how much we've yet to learn and how thrilling it is to keep searching. The universe is vast, mysterious, and far stranger than we imagine, and that's the best